Hey there, STEM Chemistry. This is Ms. Ruark. Now we're going to talk about the molecular geometry of the compounds that we've been dealing with. And I'm going to show you a couple more things about Lewis structures before we get started on the geometry. But the geometry is also important, so we'll get to that too. Okay, so when you're writing a Lewis structure for a substance, sometimes you'll run into this thing we call resonance. And resonance happens when two or more Lewis structures can be written, but you can't really tell what the correct structure is. You can't give the actual correct structure because it can possibly have two or more. Okay, now these, well, let me explain to you. The reason there can be two or more is because you can have either what we would call functional groups or electrons put in different places, and it doesn't mean it's wrong. It just isn't 100% correct. All right, so when you're writing these resonance structures, all of them must have the same skeletal structure. So they must all be similar as far as the skeletal structure is concerned. And when you write them, you would show all structures and you would join them by a double-headed arrow. All right, so what in the world does that mean? Well, let's do the Lewis structure for O3, which is ozone. There are 3 total oxygens, and each oxygen brings a total of 18 electrons. So 18. They bring 6 electrons for a total of 18. That's where I got it from. All right, now we have our 3 oxygens, and you can't actually put them in a triangle like this. That doesn't work. Yeah. So if you tried that, good try. But you can't put them like that. You would actually have one of them in the middle, and then the other 2 would be on the outside. Okay, so when you draw your skeletal structure, you should have something similar to this. We've used a total of 4 electrons, which means that we have 14 to go. All right, now to make these happy, this one would need 6 more, this one would need 4 more, and this one would need 6 more. Okay, so that would give us a total of 16 that we would need. Now, if you remember when we did our double and triple bonds, we said, hey, if we need more than we have in our bank account, they need to share another one. So we need to come back through and fill in another one. And I told you, it doesn't matter which side you put it on, right? Well, now this is where this resonance, that's where it comes in. Because if we put it here, it's correct. If we put it over here, it's correct. It really doesn't matter. Okay, so let's go back and let's change our numbers here because they have just been affected, correct? So this one now, we've used 2 more. Don't forget to subtract from your bank account. You don't want to overdraw. Whew. Important life lesson there. Okay, so here this one has 4 electrons. It needs 4 more to be happy. This one has 6. It needs 2 more to be happy. And this one has 2. It needs 6 more to be happy. So we have now used, or we now have 4 plus 2 is 6, plus 6 is 12. We need 12 to make this compound happy. And look, we have 12 in our bank account. So we're going to come in and we're going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, ozone is happy. However, this isn't the only possible structure that we could have, correct? We could also have, some of you may have done it like this. And you say, but isn't that the same thing? Well, it is the same thing, but it's not the same thing because it's the way that it presents itself to the other things that it's going to bond with. Okay, and you'll notice as we do more resonance structures in class that you'll see there is an actual difference between these when we go through. So when you draw them, you'll have to draw both of them, and you'll show them with this double-headed arrow here to show that these 2 have resonance. Okay? And it doesn't mean that it stays in this one form and then it flips to this one form and then it goes. No, it doesn't do that. It just means that these are possible ways that these could be shown, but the electrons are actually just kind of hanging out. And I'll talk more about that in class. All right. Let's see, exceptions to the octet rule. So we have a couple exceptions to the octet rule that you'll need to make sure that you remember. We have small atoms like boron, and boron would actually prefer, instead of having an octet, it would rather have a sextet, I guess is what you would call it, 6. Right, so boron actually likes to be like boron trifluoride or boron trichloride, and it would be a boron in the middle, and it would have the three of whatever it is it's attached to coming off the outside, because boron has 1, 2, 3 valence electrons, and it's attached to, let's say, chlorine. There are 3 of them with a total of 7 valence electrons. So that would be 3 plus 21 gives us 24, right? If we subtract these 6 that we've used already, we now have 18 left. Well, guess what? We need 6, we need 6, and we need 6. So 6 times 3 is 18, and so now everybody's happy because they all have the right number of valence electrons. Okay, so boron is one of those that likes to make just 3 bonds instead of 4. You also have your phosphorus and your sulfur. Some of the 3p block elements like to have, they like to dip into their d orbitals, and they can make actually more bonds. They can be, oh, what's the word that goes there? I know what it is, but I can't think of what word I wanted to put there. Hold on, I'm looking for it. And of course, I'm not going to be able to find it. Expanded. Ha! I know, right? Mr. Rick, you should have known that. All right, and they can be expanded, which means they have more than 8. So for an example here with PCl5, you would have phosphorus in the middle, of course, and then you would have your chlorines coming off Cl, 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 and they would all have dots around them. Phosphorus is happy now. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. You can also have phosphorus trichloride, where you would have the phosphorus in the middle and you would have your chlorines coming off. Okay. On this one, phosphorus would actually like to have more because it either has to have an octet or it can take on more. It just expands and grabs more, but it has to have the 4. Okay. You can also have sulfur. Sulfur likes to get all crazy and take on 6. Oh, I know. Sulfur is the life of the party here. All right, so in sulfur, it would be attached to 6 fluorines. Woo! Right, and then each one would have their 6 dots around them. And sulfur, you're not going to add more, just like in, oh, I put too many on that one, sorry. Just like in phosphorus, you're not going to add any extra in here. It can take on more, but it's not going to have any free-floating valence electrons on it because they're bonded. All right. Lewis structures of polyatomic ions. So same rules apply as always, but now you're going to take and put the Lewis structure in brackets to show the charge for the ion. Okay, so for NH4, nitrogen brings 5 valence electrons, and then hydrogen brings, there's 4 of them, and they each bring 1, which gives us a total of 9. All right, so when we draw this out, nitrogen goes in the middle, 2, 4, 6, 8. Who do we appreciate? Sorry, couldn't help it. All right. Is that right? 5, 6, 7, 8, 9. Okay. 2, 4, 6, 8. And then we've got hydrogen, we've got hydrogen, we've got hydrogen, we've got hydrogen. Okay, so we've got 2, 4, 6, 8. Everybody's happy. We have 1 extra electron here, but guess what? That plus there tells us that we need to subtract 1 extra electron from it. So there should be 1 extra electron left over, right? All right, so then to show this, we would show that this right here has a positive 1 charge. Okay, another way to do that is you could go on ahead and add up your 5 plus your 4 times 1, and then you can say, hey, we've got 1 electron that's going to go away, so we would subtract 1, which would show us how many total we're going to be messing with. Okay, either way, we're going to practice these in class just in case you got a little confused on that one. Okay, molecular geometry. So molecular geometry just shows the 3-dimensional structure of a compound. Now we have this thing called the VSEPR theory. It's the valence shell electron pair repulsion theory, and it guides the shapes of all the molecules that we have. What does this say? Well, it just says that these negative charges of the electrons repel each other. They don't like to be near each other. And they repel each other away, creating molecular shapes where the electrons are going to be as far away from each other as possible. And that's how we get the geometry for these shapes. So what can they be? We could have a tetrahedral, which is where the electrons that are outside, or these hydrogens right here are bonded to this carbon by these electrons. And these electrons here in these bonds don't want to be close together. They hate it. They want to get as far away from each other as possible. So they're repelling each other. They're pushing, 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 going backwards and pushing away as far away from each other as they can be. And that's what makes the tetrahedral shape. I'll see if I can find molecule kits and we'll play with these. All right, we can also have the trigonal pyramidal, which is, or trigonal pyramidals. It depends on how you say it. All right, and that would be an example of ammonia here. Ammonia has the bonded electrons, which are shared, and then there's a free pair of electrons here, and they all repel against each other. They're pushing away from each other as much as possible. Then you have your bent. An example of that would be your water molecule. You have a bonded pair here, a bonded pair here, free pair of unbonded electrons, and they are all pushing away from each other. Notice they're all similar in shape. Oh, yeah. Okay, but they're all pushing and pushing away as much as possible. And then you have your linear. An example of that would be carbon dioxide. You would also have hydrogen fluoride, where you have these electrons that are pushing away, and it ends up being a linear shape to it. Okay, there are actual what am I thinking of? Bond angles that we'll need to pull in here, and we'll talk about them when you get into class. The last one that we're going to be worried about is called the trigonal planar or trigonal planar, and that's where you have the central atom does not have any free or lone pair electrons on it, and therefore you just have the three bonds, or the three sets of bonds that are pushing away from each other. So you just have three, as opposed to here where you have that fourth pair right there pushing away. Okay, and we will play with these as well. All right, and that's it. So I will see you in class.